Hello everyone! It is time for me to get more into the electronics world, and today I'll be doing more and more complicated LED projects, starting with a single LED. I had an electronics learning kit in my drawer that has been sitting there for a few years, and I randomly decided today is the day. It has a bunch of things inside, but this time I'm only interested in lamps. We start with a single LED because not only do I need to verify that my awful soldering works with this poor Raspberry Pi, but it is basically the minimal possible circuit. Or is it? What is the most simple electronic circuit possible? This is the most simple electronic circuit. You take the plus wire and connect it to the minus. Simple. And then you get an explosion. But why? I think it is worth understanding basic concepts before starting to do any of this. I will be working with safe current for now, but that might not be the case later. Anyway, the first reason for an explosion like this is heat. You probably know that transferring current causes heat to build up in the wires. With enough current flowing, the wires get really hot. How hot? Plasma hot. Turns out, if there is nothing in the circuit to limit the current, like connecting the opposite terminals such as live and neutral in a wall socket directly, the current can heat the metal so much that it starts to melt, or in even higher voltage systems even boil. This was an interesting realization for me. In the context of what we will be doing, the microcontroller has only limited protection against shorts, aka connecting the opposite terminals directly, so an individual pin or another part of the circuitry might burn. It wouldn't explode, but it's still pretty bad news. To avoid overheating, we need to use resistors. We will be using this type of resistor, which is 220 ohms. I will not get into formulas, and in simplest terms, resistors resist current. They limit how many electrons can pass through the circuit, and in turn, not only less current passes through the circuit, but the heating effect we talked about is proportionally smaller. You might have a question at this point. Why don't they design the power sources so that they don't need resistors? And while technically that is possible, it is very impractical. You see, if your wall outlet, like this one, was only powerful enough to power a lamp, then it definitely would not be able to power a kitchen stove. Instead, devices themselves are designed so that their internal resistance or circuitry determines how much current they draw. This way, small appliances draw little power, while large ones can draw much more. This works because the electrical infrastructure provides enough capacity for high-power devices, and devices themselves limit the current with internal resistance if needed. The same idea applies to microcontrollers. LEDs need resistors because on their own they would allow too much current to pass through and burn up because the microcontroller supplies more than needed for the LED, while other components, like motors, naturally limit their current in different ways and don't need the same protection. It's all done for practicality and versatility and allows the use of different components with the same power source. The LEDs themselves glow when current passes through them. We won't get into more detail here. Also, we will be using this board with holes called a breadboard. It's called that due to some electricians not cutting bread but playing with electricity instead. It is connected like so in columns, and the blue and red lines also indicate where it is connected underneath. Current passes through the entirety of the connected line. Finally, the microcontroller we are using is called Raspberry Pi 2040 0. I chose it because it's cheap and supports both Python and C++. With all this knowledge, it's time to forget everything and just YOLO it. One LED. Let's go! We'll just start by connecting the microcontroller to my computer, which produces 5 volts. If you notice, I did some terrible soldering here, so how do I know I didn't mess up? Well, now I can't really know it for sure, but what we can do is test if it's supplying any power. There's probably hard to see with my camera, but we have 2 pins here, as you can see, 5 volts and ground. So this supplies the current, and this is the ground where the current goes back to. So what we can do is to actually complete a circuit and place something in the middle so we can see if that thing is working as expected. And what we'll use for that is an LED, of course. So I'll grab a red LED and we'll place it somewhere. Right here. Unfortunately, I can't just plug it in since it will just basically blow up, or rather just go out. It will burn up inside. So I'll connect the resistor at the same line here, this one, and place the pin for now to here. So of course nothing happens, it's not connected anywhere, but we just prepared the circuit. So right now somehow we need to bring the 5 volts out of the microcontroller to this LED, and we will use some jumper wires. That's not good. So I have connected the 5 volts, and after connecting it we can use this connected line marked with plus, nothing to do with plus really, but we can use this line since it's all connected to transfer the 5 volts into here. So it's going through the resistor, it's going to an LED, but from there it doesn't go anywhere. So now we need to complete the circuit. So from 5 volts we need to connect back to the ground. So I will plug a blue wire to the ground, and we can place it after an LED, and as you can see it lights up. We haven't really done any sort of, I guess, programming or anything of the sort, but we did complete the circuit, so we know that the microcontroller does have power. So this is good. Now, what we can do with it is, instead of transferring power directly from the 5 volt pin, which will always produce 5 volts, we can try to transfer it from one of the other pins. Let's say we have over here pin number 4, and the same way we plug it in here. It doesn't really matter which hole I'm using, it's not really very easy to plug in, but so now of course nothing happens, and this is the part where we need to use our computer. We can write some basic code to tell the microcontroller to basically produce 5 volts at that specific pin so our LED can light up. So let's try to do it. I wrote some basic code that operates on pin 4, the pin that our LED is connected to. The code runs in a loop. First, it enables current flow from pin 4 to the LED. It then waits for 1 second. After 1 second passes, it disables the pin. It waits for 1 second again, and the cycle continues. Simply said, it just makes the LED blink in 1 second intervals. So, what I want to do now is to add more LEDs, so we sort of create like a garland, or I don't know, that's how it's pronounced. Garland, anyway, let's do it. To support 3 LEDs, we need to slightly modify our code. Instead of 1 pin, we declare 3 of them, all assigned to a different number. To have the same pattern, in a loop, instead of enabling and disabling 1 pin, we do it for 3 pins. Everything else is the same. After connecting the circuit, it was time to test the code, and I was running into some problems. Nope. Is it not connected to the ground? Like, what is going on? Oh. You have to be really thorough on how you connect these wires, because they definitely sometimes just don't work, or you think you plug them in but you didn't. So right now we have a setup that makes 3 lights shine for 1 second, and then all 3 of them turn off for 1 second. I would like them to light up only 1 at a time and repeat. After once again modifying our code, we had some lovely Christmas lights. I was already so excited with what I had, and I felt that it was a good time to introduce more complexity with something like this. I think this is called a 7-segment display. It has basically 7 LEDs inside. Actually, it's an 8. It's 8 LEDs, I guess, because it also has a dot. So we have 1, 2, 3, 4, 5, 6, 7. Yeah, 8 LEDs basically. So we will need to do for all of these 8 LEDs, actually the same setup, and it has 10 pins in total, basically 4 pins on each side for the LEDs, and the middle pin is the ground. So we don't need actually these wires for each LED to go back to the ground. We can just use the one middle pin for the entire, I guess, device, if this can be called that. So I'll get the setup and then we can come back. So we have current and ground connected, and we can see the red wire. From here the current goes to here, it goes into resistor, goes through the resistor, comes into LED, and then if we connect the ground, same as before, the LED lights up. Here I have created a little bit of a spaghetti mess, but this type of sign actually works the exact same way. So instead of one LED, we have 8 LEDs, and just the same way they are all connected with resistors. We'll have 1, 2, 3, 4, 5, 6, 7, 8. And now if we connect the ground, which is the middle pin, I will probably show it on the screen so you understand how this is all connected. But if we connect the middle pin to the ground, you can see all 8 of the LEDs light up. I wonder why it's called a 7 LED sign if there's 8 of them. I guess previously there wasn't a dot. Anyway, it's good. We can light each LED, and for example, if I disconnect current to, like, let's say one of them, you see it goes out. So now what we want to do is to set up each of these LEDs to a separate pin so we can control each of them independently, similar to how we did it with the 3 lights before. Connecting them to the microcontroller will allow us to achieve the primary function of the display, to display numbers. By the way, this is the IDE I was using for programming the Raspberry Pi. Unfortunately, my video recording settings were shit by accident, so this is what we're stuck with for the video. You can see me changing what number appears on the LED screen live by changing the number that I passed to the show digit function and running the code on the microcontroller. The way this code works is that we hard code LED combinations for each number in advance. We can define a function that lights up specific combination of LEDs based on the number we requested to light up. If we make the numbers change in a loop from 1 to 10, with 1 second delays, we essentially create a 10-second timer. At this point, I was getting hooked on this. A realization hit me that theoretically, I can create any electronic device I want right here in my home. Of course, I won't pretend I am smart enough to create them, and this video will be limited to using this final device. Ta-da! I have something new here, and shiny. So what this is a 8x8 LED matrix. I have absolutely no idea how all of this is connected, but I assume I won't have to use 64 resistors, and I don't even have that much of them. And it has only like 12 pins or something. It's like 16 pins, and it's 64 lights. I'm not sure if these are controlled by sort of 4 lights at once, or there's like some sort of combination of the signals you have to activate to light each LED individually, but I guess we will see that. So I'm not even sure if I have any way of wiring this up easily. Oh, it takes up the entire board. So I guess I will need to, well, there is physically just no way I can plug any of the jumpers to the columns that I'm using with this matrix. So I'll have to order some breadboard that allows me to basically continue working like this. So see ya when I get the goods. Unfortunately for my breadboard, I was not patient enough to get the goods, and I came up with a different solution. We have a problem with this LED matrix and the breadboard. When I connect the LED matrix to the breadboard, there isn't any space left for me to put the jumper wires or connect anything. So if we look behind the breadboard, So, behind the breadboard, there are these lines, which are basically how the breadboard itself is connected. So you see we have these columns here, and basically they're connected like columns like that. And in the middle there's like a spacing. So I think this is going to need an upgrade, and I have a very special upgrade kit for this, which is gonna work perfectly. And we're gonna upgrade it by cutting it in half, because I see no other way. So I'll just cut it. So what this did is now we can connect one side like this, and we can connect the other side like this. So now there's actually space for me to connect the pins to the Raspberry Pi. Looking at this now, it's even beautiful how I was connecting everything. Don't worry, it will soon turn into a mess again. It took me quite a bit of time to get everything set up. I used a method of trial and error where I would just connect one pin to the 5 volts and then try all other pins for ground. I was slowly able to get more and more LEDs to light up. Before I finish connecting everything up, I think it's a good time to share with you what project I have in mind for this 8x8 LED display. The goal is to create an audio visualizer that is able to display patterns based on music. I wrote a Pi game simulation that represents this goal. The idea is to have a preset pattern. The louder the music, the more of that pattern is displayed. At least that was the plan originally, but I ran into some difficulties. By this time, I have already fully understood how the display is functioning. It has 8 pins that sends the current to 8 rows. Each row corresponds to 1 pin. It also has 8 pins which ground a column each. So to light an individual LED, we need to send the current to that row and ground that column. It sounds simple, but the problem is that you cannot just ground current on demand using a microcontroller like this, not without external help at least. I can't ground enough current with GPIO pins only to make the LEDs light up. And for that, we are going to use something called a Darling pair. A Darlington pair. That was invented by Sidney Darlington in 1953. Aside from fancy names, the device we will use has 10 pairs of NPN transistors that were invented by this guy. On one side of said transistor pair, you connect the thing that you want to ground on demand. In this case, it will be our column pin. On the other side, you connect a GPIO pin that is able to send current. When the current is sent from the microcontroller, the array device thingy allows grounding the pin opposite of where we send the current. This works because one of the array pins is connected to the ground. In some way, it is able to do this without any moving parts. Honestly, this is weird for me, and I think it's best not to look into what black magic is used inside this darling. Enough physics for me today. Having it on my table after it arrived, it's just a black box with a bunch of pins. Since I already knew how the LED matrix works, I was able to easily reconnect everything, and here is the final configuration I was using. It was starting to resemble those meme pictures about badly managed server rooms, but hey, at least I understood how this works. Having fully connected the LED display, the only thing left to do was to write the code. I will not go through the entire thought process, and instead we will just take a look at the final solution I came up with. First of all, we need a sound file to represent. For that I will use a wave audio file. The wave file is essentially a bunch of numbers ranging from -1 to 1, and we can represent them in a wave. We will split the wave into pieces and with the help of code calculate how many LEDs should be lit up for that specific piece. After doing it for the entire wave file, we can put these values into another file and upload it to the microcontroller to start the visualizer. These patterns themselves will be hard-coded, and this is relatively simple. Say all lights have indexes ranging from 0 to 63. We create a pattern that contains all 64 values in order, the order in which LEDs will light up. If we need to light 5 LEDs, it reads the first 5 values from this pattern array and lights the LEDs with those 5 numbers. If we had to light 32 lights, it would do the same with the first 32 values. Examining the main loop that will perform the light show, it will go as this. It will read a value from the file that we generated previously. That value will contain a number of LEDs that we need to light up. Based on this number, we will read that many values from the pattern array. And we'll light the corresponding LEDs from that array. This will be done 30 times each second until the file ends. Another thing to take note here is that LEDs don't all shine at the same time, because they can't. 64 LEDs actually draw quite a good amount of current, and since we don't have an external power source, if they stayed on for long, the microcontroller would likely get fried, so the program also features multiplexing, which is just a fancy way of saying we light each row for a short amount of time. It all happens so fast you can't really notice it with naked eye. In code, we premap the pattern for each frame by creating a dictionary with row pin indexes as keys and column lists as values. During one piece of the song, which for us takes 33 milliseconds, we iterate through all row pins. For each pin, we enable current, then we check if our pre-computed map for this frame contains the current row as an index. If it does, we light all the columns needed. We wait for 0.002 seconds and turn all LEDs for that row off. And we do that for all rows. The final code came a little more complicated than I had hoped. Nonetheless, I was getting really excited when programming this, and I'm very happy to share the final result. For a final version of this, I would love for it to read audio signals via Bluetooth, as it is played on a device like a mobile phone, and for it to be a separate rechargeable device disconnected from my computer completely. But for now, I want to just be happy with what I achieved.
Good.
Is it good?
Mm-hmm.
Overall, I'm very happy with how the project turned out, and I'm proud of myself. Now, I won't say it was perfect, because I had to do things such as speed up the video to actually match the audio it was playing, but I'm still happy at the end. And for you, you absolute beasts who stuck with me till the end of the video, I want to say thank you. Hopefully you found it interesting and maybe even learned something new. I want to wish happy holidays to everyone, have a good rest, and I'll see you next time. See ya!